What would the universe look like if you could ride a beam of light? It's a question Albert Einstein first imagined as a teenager, not as science fiction, but as a genuine thought experiment. What would it mean to move at the speed of light? Would time freeze? Would distances vanish? Could you even see anything at all? The answer is not just counterintuitive, it's deeply revealing, because asking what happens at the speed of light leads us straight to the edge of physics itself. It forces us to rethink everything we take for granted about space, time, and even causality. Tonight, we're going to follow that question all the way through. From the earliest debates about the nature of light to Einstein's special theory of relativity, from the mysteries of time dilation to the paradoxes of simultaneity, from quantum probabilities to modern particle accelerators, GPS satellites, and the fabric of space-time itself. Let's begin. If you sit quietly and observe your surroundings, it may feel as though the world is still. The ground beneath you is unmoving. The furniture doesn't drift. Even the air, unless stirred, seems to rest in place. Motion, to our everyday senses, is something we do, something we initiate. We walk, we run, we move cars, trains, and aircraft. But beneath that calm perception lies a more complex truth. Nothing in the universe is truly still. Stillness, as it turns out, is an illusion. For most of human history, the natural assumption was that motion was something absolute. Either you were moving or you weren't. This idea is intuitive, and it matches how we experience the world. But in physics, what feels intuitive is often misleading. To see where this journey begins, we travel back to the early 17th century, when Galileo Galilei, the Italian scientist and astronomer, began challenging ancient assumptions. At the time, the dominant framework for understanding motion came from Aristotle, whose writings had shaped natural philosophy for nearly 2,000 years. According to Aristotelian physics, objects moved only when a force acted upon them, and they naturally came to rest when the force stopped. It was an appealing explanation. Push a cart, and it rolls until friction stops it. Throw a stone, and it arcs and falls. But Galileo saw deeper. Galileo's key insight was that motion is relative. In his famous thought experiment, he described a ship moving smoothly across calm seas. If you were in the ship's cabin, below deck, with no windows, you would have no way to tell whether the ship was moving or stationary. A dropped ball would fall straight down. A butterfly would hover as if in a still room. To the observer inside, the motion of the ship was undetectable, without reference to something external. This was not just a clever analogy, it was a profound statement about the nature of physical laws. Galileo proposed that the laws of motion were the same for all observers moving at constant speeds relative to one another. This was the beginning of what we now call the principle of relativity, and it would later become the foundation of Einstein's special theory of relativity. Galileo's version was limited to mechanical systems, but the seed had been planted. In Pisa, and later in Florence, Galileo conducted experiments, rolling balls down inclined planes, measuring time with water clocks, and charting the behavior of pendulums. What he found consistently was that objects in motion tended to stay in motion, unless something interfered. This directly contradicted Aristotle's idea that rest was the natural state of matter. Galileo's work laid the groundwork for Isaac Newton, who, later in the 17th century, formulated the laws of motion and universal gravitation. Newton's first law, often called the law of inertia, states that an object in motion stays in motion at a constant velocity, and an object at rest stays at rest unless acted upon by a net external force. In other words, rest and uniform motion are essentially the same thing from a physical point of view. There is no experiment you can do inside a smooth-moving vehicle to prove whether you're moving or not. This idea may seem abstract, but it has direct consequences. For example, as the Earth orbits the Sun at roughly 67,000 miles per hour and rotates on its axis at about 1,000 miles per hour at the equator, we feel none of this motion. Standing still on the surface of the Earth feels, well, still, but it is not. We are passengers on a rotating, orbiting, moving planet, and it does not stop there. The Sun itself is moving around the center of the Milky Way galaxy at an even faster pace, more than 500,000 miles per hour, dragging our entire solar system with it. Stillness is not only rare in the cosmos, it may not exist at all. Yet this raises a deeper question. If all motion is relative, then relative to what? Before the 20th century, many scientists believed there must be some kind of invisible background, a medium that defined absolute rest. Just as sound requires air to propagate, light too was thought to need a medium. This hypothetical substance was called the luminiferous ether. It was imagined to fill all of space, providing a fixed frame of reference against which motion could be measured. If you moved through the ether, you should be able to detect its presence. That belief led to one of the most important experiments in the history of physics, the Michelson-Morley experiment of 1887. But before we go there, it's essential to recognize what this belief in the ether represented. It was, at its heart, a return to the idea of absolute motion. Despite Galileo's insights, many physicists remained uncomfortable with the notion that there was no fixed frame. The ether was an attempt to restore that comfort, to give light a medium and to provide the universe with a sense of absolute stillness. But the groundwork had already been laid for a different understanding. By the end of the 19th century, James Clerk Maxwell had unified electricity and magnetism into a single theory, electromagnetism. His equations described how electric and magnetic fields oscillated together to produce light. These electromagnetic waves didn't require air or wires to travel. They moved through empty space. The equations predicted a specific speed of light, and that speed appeared to be the same in all directions, regardless of any presumed motion through an ether. This created a tension. If light always moved at the same speed, even when the source or the observer moved, then how could that be explained? According to classical physics, if you walked toward a light source, you should measure its speed as faster than if you moved away from it. Just as the sound of an approaching car is different than one moving away, light should behave similarly. But it didn't. Scientists needed a decisive test. That test would come in the form of an ingenious optical experiment, using rotating mirrors, split beams of light, and the movement of the Earth through space. But to appreciate why that experiment mattered and how it disrupted centuries of thinking, we first need to understand the full significance of what it tried and failed to detect. The idea that motion is always relative and that no experiment can determine your absolute velocity sounds simple on the surface. But once light is involved, the implications become extraordinary because light behaves differently than sound. It doesn't slow down in fog and it doesn't speed up toward you. It seems to be absolute, unchanging. And that is the crack in the classical worldview that opens the door to relativity. The illusion of stillness is not just a sensory trick. It is a clue, a hint that motion and rest are not fundamental categories, but interchangeable states. Galileo's moving ship was not just a metaphor, it was a gateway into a new understanding of the universe, one where motion is relative, but light might be something else entirely. But if light moved at a constant speed, even when the Earth itself was in motion, then through what exactly was it moving? What medium, if any, allowed that motion to happen? And why did that medium seem completely undetectable? To make sense of this mystery, we have to step back to a time when the nature of light was still under heated debate. Long before the modern concept of particles and waves was clear, light was already a subject of philosophical and experimental curiosity. From ancient Greek thinkers like Empedocles, who suggested that light traveled at a finite speed, to later figures such as Pythagoras and Aristotle, opinions differed. Some believed light traveled instantaneously. Others speculated it was a form of motion, though what exactly was moving, and through what, remained obscure. In the 17th century, Galileo Galilei attempted to measure the speed of light. His method was simple but ingenious. Two people would stand at a distance, each with a lantern. One would uncover their lantern, and as soon as the other saw the light, they would uncover theirs in response. By measuring the time delay, Galileo hoped to detect how fast light traveled. But even across distances of several miles, the response seemed instantaneous. Galileo concluded only that light was extraordinarily rapid, but too fast to measure with the tools of his time. It It wasn't until the mid-17th century that Danish astronomer Ole Rømer provided the first quantitative estimate of light speed, indirectly. In 1676, while studying the eclipses of Jupiter's moon Io, Rømer noticed a strange inconsistency. The timing of the eclipses varied depending on Earth's position in its orbit. When Earth was moving toward Jupiter, the eclipses arrived sooner. When Earth was moving away, they arrived later. Rømer correctly interpreted this delay as due to the finite speed of light. His observations suggested that light did not travel instantaneously, but rather at a measurable, though extremely high, speed. From this point onward, the idea that light had a finite velocity gained wide acceptance. Over time, the estimates became more accurate. By the mid-19th century, experiments by Hippolyte Fizeau and Léon Foucault using rapidly rotating mirrors and toothed wheels managed to bring light's measured speed close to the modern value, roughly 186,000 miles per second in a vacuum. But while the question of light's speed began to settle, a deeper question emerged. What was light actually made of? By the early 19th century, a series of groundbreaking experiments pointed toward wave-like behavior. Thomas Young's double-slit experiment, performed in 1801, showed that light could interfere with itself, creating bright and dark fringes when passed through two narrow slits. This was a hallmark of wave behavior. In subsequent years, Augustin, Jean Fresnel, and others developed a mathematical theory of light as a transverse wave. This view challenged Isaac Newton's earlier belief that light consisted of particles, or corpuscles. But waves, by their very nature, require a medium. Sound waves need air. Water waves need water. So if light was a wave, then what was the medium through which it traveled? The vacuum of space offered no obvious material for the wave to ripple through. To solve this dilemma, physicists in the 19th century proposed the existence of a new kind of medium, the luminiferous ether. This substance was imagined to permeate all of space, even in regions devoid of matter. The ether was not made of atoms, nor did it interact with ordinary matter in any detectable way. Yet, it was thought to be essential for the propagation of light. The ether needed to have peculiar properties. It had to be incredibly rigid to support the high frequency of light waves, yet undetectably light and frictionless, so it wouldn't slow down planets or objects moving through it. It had to be stationary in space, providing a fixed frame of reference. The Earth, then, must be constantly moving through this stationary sea of ether. This idea led directly to the expectation that one should be able to measure an ether wind, an effect caused by Earth's motion through the ether, just as you might feel the wind on your face while running. If the ether existed and light moved through it, then the speed of light should vary depending on the direction of Earth's motion. In principle, one could detect the difference by measuring how long it took light to travel in various directions, similar to how the time it takes to swim across a river changes depending on the current. Enter Albert A. Michelson and Edward Morley. In the 1880s, Michelson, a physicist born in Prussia and raised in the United States, became obsessed with the idea of measuring the ether wind. He was joined by Edward Morley, a chemist with a strong interest in physics. Together, at Case Western Reserve University in Cleveland, Ohio, they devised an experiment to detect the Earth's motion through the ether. Their apparatus, completed in 1887, was a marvel of precision. It used a device called an interferometer, essentially a system of mirrors and split beams of light designed to measure tiny differences in the time it takes light to travel along perpendicular paths. The principle was simple. If the Earth was moving through the ether, then the light moving with the ether wind would take slightly longer to return to its source than the light moving at right angles to it. This difference would show up as a shift in interference patterns when the two beams of light were recombined. The device was mounted on a stone slab floating in a pool of mercury, allowing it to rotate smoothly in all directions to test different orientations. The results, however, were utterly unexpected. They found nothing. No matter how they rotated the device, no matter what time of day or year they tested, there was no detectable difference in the speed of light. The interference fringes remained stubbornly fixed. The expected shift due to the ether wind simply did not appear. This result shook the foundations of physics. If the ether existed, it should have revealed itself in this experiment, and yet, it remained elusive. Michelson and Morley were not able to explain the null result, but they reported it with meticulous care. For their efforts, Michelson would later become the first American to win the Nobel Prize in Physics, though not for this experiment specifically. The failure to detect the ether forced physicists to consider increasingly convoluted theories. Some proposed that objects moving through the ether physically contracted in the direction of motion, an idea suggested by George Fitzgerald and later developed mathematically by Hendrik Lorentz. According to this view, the interferometer itself shrank just enough to cancel the time difference. Others speculated that the ether was somehow dragged along by the Earth, making it undetectable from the surface. None of these explanations were entirely satisfying. They all involved adding layers of complexity to preserve the idea of the ether. But the central problem remained. No experiment had ever directly observed this mysterious medium. Meanwhile, another revolution was quietly brewing. In the background, James Clerk Maxwell's equations had unified electricity and magnetism into a single framework, known as electromagnetism. Published in the 1860s, Maxwell's equations described how electric and magnetic fields changed over time and how those changes propagated through space. Crucially, these equations predicted that electromagnetic waves, including light, would travel at a specific speed, about 186,000 miles per second. But Maxwell's equations didn't reference the ether at all. The speed of light, according to these laws, was a property of the electromagnetic field itself, not of any surrounding medium. That raised an unsettling possibility. Perhaps light did not need a medium at all. Perhaps the ether, so long assumed to be essential, simply didn't exist. By the dawn of the 20th century, physics was at a crossroads. Classical mechanics worked well for planets, projectiles, and pendulums. Electromagnetism beautifully explained light, electricity, and magnetism. But there was a rift between the two frameworks. The principle of relativity, rooted in Galilean thinking, said that all uniform motion was equivalent and that the laws of physics should be the same in all inertial frames. Yet Maxwell's equations seemed to treat the speed of light as special, unchanging, no matter the observer's motion. This contradiction could not stand forever. What began as a simple question, how does light move, had unraveled into a crisis at the heart of physics. The failure to detect the ether was not just a setback, it was a turning point. It forced a deeper re-examination of the assumptions underlying space, time, and motion itself. Faced with mounting contradictions and an experimental result that refused to align with long-held assumptions, physics stood on uneasy ground. The ether had been an essential pillar of 19th century science, a quiet, invisible presence that explained how light could travel through space. But when the most precise measurements of the era found no trace of it, the question became unavoidable. What if the ether was never real to begin with? In the years following the Michelson-Morley experiment, physicists struggled to interpret its implications. The failure to detect the Earth's motion through the ether was not brushed aside. It was deeply unsettling. Many found it difficult to accept that space could be truly empty and still support the motion of light. Rather than abandon the idea of the ether altogether, some turned to increasingly elaborate theories to preserve it. One such theory came from Irish physicist George Fitzgerald. In the late 1880s, Fitzgerald suggested that perhaps objects moving through the ether physically contracted in the direction of their motion. This length contraction, as it came to be known, would cause the measuring apparatus in the Michelson-Morley experiment to shrink just enough to cancel out any differences in light travel time. It was a clever proposal, though entirely hypothetical. Soon after, Dutch physicist Hendrik Lorentz independently developed the same idea and gave it mathematical form. Lorentz had already been working on the equations that governed electromagnetic phenomena, and he realized that if space and time coordinates were modified in a specific way, Maxwell's equations could remain valid for moving observers. These transformations, now called Lorentz transformations, described how time and space must behave if the speed of light remained constant for all observers. But this solution came with a strange price. It implied that time itself might behave differently for observers in motion. Lorentz himself still believed in the ether. He viewed these mathematical transformations as corrections for how objects behaved as they moved through the ether, rather than as a redefinition of space and time. In his view, the ether still existed. It was simply undetectable due to these compensating distortions. The theory seemed increasingly strained. By the turn of the century, the scientific community was still hesitant to let go of the ether, but the cracks in its foundation were widening. The more experiments failed to detect it, the more convoluted the explanations had to become. And meanwhile, Maxwell's equations continued to predict light's behavior perfectly, without ever mentioning the ether at all. Into this landscape stepped Albert Einstein. In the year 1905, while working at the Swiss Patent Office in Bern, Einstein published a paper titled On the Electrodynamics of Moving Bodies. It was one of 4 groundbreaking papers he released that year, later called his Annus Mirabilis, or Miracle Year. But among them, this particular paper would redefine the very structure of physical reality. Einstein's bold move was to let go of the ether entirely. Rather than assume that space had a hidden structure through which light moved, Einstein asked a different question. What if the laws of physics are the same for all observers in uniform motion? And what if the speed of light is the same for all such observers, no matter how fast they are moving? These 2 postulates became the foundation of what is now called the special theory of relativity. The first postulate, the principle of relativity, was not new. Galileo had stated something similar centuries earlier. It held that no experiment could determine whether you were at rest or moving at constant speed. Einstein extended this idea not just to mechanics, but to all of physics, including electromagnetism. The second postulate was more radical, that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. If you were racing toward a beam of light or away from it, you would still measure its speed as the same. This was not a result of experiment, though experiments like Michelson-Morley strongly supported it. It was a starting assumption, a postulate that Einstein treated as a fundamental law of nature. From these 2 principles, everything else followed. If the speed of light was always constant, then time and space could no longer behave the way Newton had described them. They had to be flexible. Time had to dilate, slow down for moving observers. Length had to contract, shrink in the direction of motion. And simultaneity, the idea that 2 events can occur at the same time, could no longer be universal. What one observer sees as simultaneous, another may not. But the most important consequence, at least for the moment, was this: the ether was no longer necessary. Einstein's theory made no mention of the ether. It required no invisible medium, no preferred frame of reference, and no special substance filling all of space. Instead, space itself was a geometric stage, and light moved through it not by vibrating a medium, but as a natural result of the electromagnetic field. The structure of space-time, something that would only be fully developed later, was not anchored to a background ether, but was itself shaped by motion and energy. This idea did not gain immediate acceptance. Einstein was young, relatively unknown, and working outside of the traditional academic institutions. Many physicists were still attached to the concept of the ether, and Einstein's approach felt both too radical and too simple. But over time, evidence accumulated. One crucial piece came from the way Einstein's theory naturally explained the results of the Michelson-Morley experiment. Without needing to invoke ad hoc length contractions or undetectable media, the theory predicted that all observers, regardless of their motion, would measure the same speed of light. The null result of the experiment was not a failure, but exactly what should happen. Another piece came from the emerging field of particle physics. As researchers began studying particles moving at high speeds, especially in early particle accelerators, they found that time dilation and length contraction were not just theoretical, they were measurable effects. Particles called muons, created by cosmic rays in Earth's atmosphere, decayed more slowly when moving at high speeds, allowing them to reach the surface instead of vanishing high above. These observations matched Einstein's predictions and defied classical expectations. By the 1920s and 1930s, the special theory of relativity had become widely accepted, and with it, the concept of the ether quietly disappeared from mainstream physics. Some physicists, including Einstein himself in later years, tried to reintroduce the idea of an ether in a new sense, referring not to a substance through which light moved, but to the properties of spacetime itself. In a speech in 1920, Einstein described spacetime as having physical qualities and suggested that calling it an ether might be justified. But this was a different notion entirely, one rooted in general relativity and far removed from the rigid mechanical ether of the 19th century. The old ether, the imagined substance that filled space like a fluid, was gone. Its fall was not due to a single experiment or a sudden revelation, but to a slow erosion of necessity. As better theories emerged, ones that explained the data with fewer assumptions, the need for the ether faded. It had been a useful placeholder, a bridge between ideas, but in the end it collapsed under the weight of its own contradictions. Once the ether was cast aside, what remained was something far more profound and far more unsettling. Without a universal frame of reference, without a background medium to define stillness or motion, physics needed a new foundation. That foundation would come from two simple ideas, postulates, that together redefined how we understand the universe. Albert Einstein's special theory of relativity, published in the year 1905, began not with complex mathematics or detailed experiments, but with a clean slate and a bold question. What if the speed of light is truly the same for all observers? And what if the laws of physics hold true in all uniformly moving frames, no matter how fast they go? The first of these postulates, the principle of relativity, was not entirely new. As we have seen, Galileo had recognized centuries earlier that no mechanical experiment performed in a closed system could reveal whether that system was at rest or moving at a constant velocity. Whether aboard a ship or sitting still on land, the physics was the same. Einstein extended this principle not just to mechanics, but to all of physics, including the laws of electromagnetism that had emerged in the work of James Clerk Maxwell. The second postulate, however, was deeply counterintuitive. Einstein proposed that the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the source. This was a radical departure from classical thinking. In Newtonian physics, if a car moves toward you at 50 miles per hour and throws a ball forward at 10 miles per hour, you would see the ball approaching at 60. But Einstein said that light does not behave this way. If someone shines a beam of light while moving toward you, you would still measure that light as traveling at the same speed as if the source were stationary. These two postulates seem simple on the surface, but their implications are staggering. To preserve the constancy of light's speed, something else must change. Time and space, previously assumed to be absolute, must become relative. If the speed of light is fixed, and two observers are moving relative to each other, then they must experience time and space differently. Events that appear simultaneous to one observer may not appear simultaneous to another. A moving clock may tick more slowly. A moving ruler may appear shorter in the direction of motion. Einstein's insight was that these effects are not illusions or tricks of measurement. They are real. Time itself stretches, space itself contracts. And this is not just theory. It is measurable. This was the moment when physics took a sharp turn away from common sense. The idea that time could vary depending on motion was not something anyone had previously taken seriously. Time, in Newton's words, was absolute, true, and mathematical. It flowed at the same rate for everyone, everywhere, unaffected by motion or position. But Einstein showed that if the speed of light is constant, then time cannot be. Imagine two observers, one standing still on a train platform and another riding a train at high speed. Each carries a flashlight and a mirror, arranged so that a beam of light is emitted, bounces off the mirror, and returns to its source. Both observers perform the same experiment. But here's the catch. From the platform observer's point of view, the light on the moving train has to travel a longer diagonal path because the train itself is moving forward as the light travels up and down. Yet both observers measure the same speed of light. For that to be possible, the observer on the train must experience time more slowly. This is time dilation, and it doesn't end there. The same logic leads to length contraction. If one observer sees a moving object and measures its length using light signals, the object appears shortened in the direction of motion. Again, this is not because of measurement error, it is a real physical effect. These ideas were captured mathematically in the Lorentz transformations, equations that had already existed in partial form, thanks to the work of Hendrik Lorentz and Henri Poincaré. But while Lorentz had treated them as mathematical corrections to preserve the ether theory, Einstein embraced them as a direct description of nature. They were not a fix, they were a revelation. One of the most famous consequences of Einstein's theory came as a kind of bonus, the equivalence of mass and energy. This insight, expressed in the iconic equation E equals mc squared, emerged from Einstein's analysis of what happens to an object as it gains energy. If an object emits energy in the form of light, it must lose an equivalent amount of mass. The equation showed that mass and energy are two sides of the same coin. A small amount of mass could be converted into an enormous amount of energy, a concept that would later underpin both nuclear power and nuclear weapons. At the time of publication, Einstein's work received little attention. He was only 26 years old, working at the Swiss Patent Office, and held no university position. But within a few years, scientists began to recognize the depth of his insight. The theory was confirmed indirectly by experiments involving high-speed particles and atomic phenomena. Over the following decades, experimental physics would provide increasing support for the predictions of special relativity. One early confirmation came from studies of unstable particles called muons. These particles are created when cosmic rays strike the Earth's upper atmosphere. At rest, muons decay in a tiny fraction of a second, far too quickly to survive the journey to the Earth's surface. Yet many muons do reach the ground. Why? Because from their point of view, time passes more slowly due to their high speed. This time dilation allows them to live long enough to be detected. The muon experiment became a classic demonstration of Einstein's theory in action. Another real-world application emerged in the global positioning system. GPS satellites orbit the Earth at high speeds and at altitudes where gravity is weaker. Both of these factors affect the passage of time. Without correcting for time dilation, both from motion, special relativity, and from gravity, general relativity, which Einstein developed later, GPS would quickly lose accuracy. The system must account for these relativistic effects to provide precise location data. As Einstein's theory gained traction, it forced physicists to reconsider the very structure of the universe. Space and time were no longer separate entities. Instead, they formed a unified fabric. Space-time. Events were no longer placed at a single point in space and another in time, but rather at a specific location in space-time. This conceptual leap would become central in Einstein's later work on gravity. But even within special relativity, it changed how physicists thought about causality, motion, and even the nature of reality itself. Einstein's work on special relativity did more than resolve a conflict between Maxwell's equations and classical mechanics. It offered a new way to look at the world, one in which speed, time, and space were not absolutes, but relationships. It removed the need for hidden frameworks like the ether and replaced them with something simpler and more elegant. And yet, the true strangeness of relativity was only beginning to unfold. If space and time are part of the same fabric, as Einstein suggested, then distorting one must inevitably affect the other. And in the world of special relativity, the most immediate and striking consequence of that distortion is the phenomenon known as time dilation, the slowing down of time itself for objects in motion. This is not a metaphor. It is not a visual trick or a psychological illusion. Time really does stretch. A moving clock actually ticks more slowly than a stationary one, as seen by an external observer. This is not just a theoretical idea. It has been observed, measured, and confirmed repeatedly, both in natural cosmic events and in carefully controlled laboratory experiments. But before diving into the evidence, it is essential to understand the conceptual shift that makes time dilation possible. In classical Newtonian physics, time is a constant background, flowing at the same rate for all observers. No matter where you are or how fast you move, your second is always the same as someone else's second. Time is absolute. But under Einstein's special relativity, time is elastic. It changes based on your relative motion. To visualize this, imagine two identical twins. One stays on Earth, while the other boards a spaceship and travels at speeds approaching the speed of light. From the perspective of the twin on Earth, the traveler's clock ticks more slowly. Every second on the ship takes longer than a second on Earth. When the traveling twin returns, they have aged less than their sibling. This thought experiment, often referred to as the twin paradox, is a direct result of time dilation. But why does this happen? The key lies in the invariance of the speed of light. Since all observers must measure the same speed for light, their measurements of time and space must adjust accordingly to preserve that constant. A moving observer, in order to measure light traveling at the same speed as a stationary observer, must experience time differently. The faster you move, the more your clock slows down relative to someone who is not moving with you. This effect becomes more pronounced as you approach the speed of light. At ordinary, everyday speeds, such as riding in a car or flying in an airplane, the effect is minuscule, far too small to notice. But at speeds that are a significant fraction of the speed of light, time dilation becomes dramatic. One of the most compelling confirmations of time dilation comes from particles known as muons. These subatomic particles are created when cosmic rays strike atoms in the upper atmosphere. Muons are unstable and decay very quickly, typically within a few millionths of a second. At rest, they would not live long enough to reach the Earth's surface. However, we routinely detect muons at ground level. How is this possible? From the perspective of scientists on Earth, the explanation is time dilation. The muons are moving so fast that their internal clocks run more slowly relative to the Earth's frame. As a result, they live longer than they would if they were stationary. From the muon's point of view, it experiences its normal short lifetime, but because the atmosphere is length contracted from its perspective, it reaches the surface before decaying. Either way, the result is the same. Time is not ticking at the same rate for all observers. This effect has also been tested with human-made clocks. In the 1970s, physicists Joseph Hafele and Richard Keating performed a remarkable experiment involving 4 atomic clocks. 2 were placed aboard commercial jetliners, one flying eastward and one westward, while the other 2 remained stationary on the ground. After the flights, the airborne clocks were compared to the ones on Earth. The results showed small but measurable differences in elapsed time, precisely in line with the predictions of special relativity. The moving clocks had ticked at a different rate due to both their motion and the effects of gravity, a combination of special and general relativistic effects. These findings are not just academic. Time dilation is a critical factor in the functioning of the global positioning system. GPS satellites orbit the Earth at high speeds and at high altitudes, where both special and general relativistic effects come into play. The onboard atomic clocks run faster due to weaker gravity, but slower due to their motion. Without correcting for these effects, GPS calculations would be inaccurate by several miles within a single day. The system only works because we account for the fact that time ticks differently depending on where you are and how fast you are moving. The implications of time dilation go beyond technology and experimental confirmation. They touch on the nature of aging, experience, and reality itself. Consider the implications for space travel. If we could build a spaceship capable of traveling close to the speed of light, astronauts aboard that ship could journey to distant stars and return having aged only a few years, while decades or even centuries might have passed on Earth. This is not science fiction in principle. It is a direct consequence of the mathematics of special relativity. However, building such a ship is another matter entirely. The energy required to accelerate to such speeds grows enormously as you approach the speed of light. That topic will be explored in depth later, but for now, it is enough to note that relativistic time travel to the future is allowed by the known laws of physics. The reverse, traveling to the past, is another question entirely, one that enters the realm of paradoxes and speculative theories. There is also a philosophical side to time dilation. It forces us to abandon the idea of a universal present. What one observer considers now may be in the past or future for another. Events that seem simultaneous in one frame of reference may be separated by time in another. This is more than an oddity. It means that our experience of time is not an absolute truth of the universe, but a local and relative one. Einstein himself was well aware of the implications. In a letter written after the death of his longtime friend Michel Besso, Einstein remarked that for those who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. This statement, often quoted, reflects the deep shift in thinking required by special relativity. Time is not a fixed backdrop, but part of a dynamic and interconnected whole. In classrooms, the concept of time dilation is often demonstrated with light clocks, a simple device that uses a beam of light bouncing between 2 mirrors. For an observer moving with the clock, the light travels straight up and down, But for a stationary observer watching the clock move sideways, the light must take a longer diagonal path. Since the speed of light is fixed, the only way to reconcile the difference is for the moving clock to tick more slowly. This thought experiment captures the heart of the issue. To keep the speed of light constant, time itself must stretch. The stretching of time may seem like a strange or abstract idea, but it is one of the most thoroughly tested and confirmed aspects of modern physics. It challenges our common sense, but it reflects a deeper reality, one that becomes visible only when we examine the universe with precision and imagination. Just as time stretches for objects in motion, space itself compresses. This companion to time dilation is known as length contraction, and it is every bit as real and measurable. While time seems to slow down from the perspective of a stationary observer, distances also become shorter in the direction of motion. This effect, like its counterpart, is not intuitive. It runs against our daily experiences. But in the realm of high speeds, especially as an object approaches the speed of light, the rules we are familiar with no longer apply. To see why this is necessary, we return to Einstein's central postulate. The speed of light in a vacuum is the same for all observers, regardless of their motion. If this principle is to hold, then something in our measurements of space and time must give way. As we have already seen, time stretches, but that alone is not enough. In order for moving observers to consistently measure the speed of light as constant, their perception of space must also change. The universe adjusts to protect that fixed speed. Length contraction occurs only along the direction of motion. If an object is moving rapidly in a straight line, then its length along that line appears shorter to a stationary observer. Width and height remain unaffected. From the perspective of the moving object, nothing has changed. It is the rest of the universe that appears compressed. Just like time dilation, this is a reciprocal effect. Each observer sees the other's lengths contracted. To understand how this plays out, imagine a spaceship traveling at a significant fraction of the speed of light. To its crew, the ship's length is normal, the passage of time is regular, and all systems operate as expected. But to an outside observer, say, someone on Earth watching through a telescope, the spaceship appears shortened along the direction of travel. It is not an illusion or a trick of perspective. According to that observer's measurements, the moving object really is shorter. Now flip the perspective. From the crew's point of view, the ship is stationary, and it is the universe that is moving past at incredible speed. In this frame, Earth and its surroundings appear contracted in the direction of travel. The distances between stars seem smaller, the length of the journey appears shorter, and what would normally be a trip of hundreds or thousands of light years might seem to pass in only a few years of onboard time. This is the key to understanding how relativistic travel, even without faster-than-light motion, could enable journeys to distant stars within a human lifetime. While Earth-based observers would see such trips taking decades or centuries, travelers moving close to the speed of light would experience much less time and much shorter distances. Length contraction and time dilation work hand in hand, preserving the symmetry of motion and the constancy of the speed of light. The mathematical expression for length contraction is similar to that of time dilation. Both involve a factor called gamma, derived from the Lorentz transformations. Gamma is always greater than 1 for any non-zero speed and increases rapidly as speed approaches the speed of light. The contracted length is equal to the proper length, the length measured in the object's rest frame, divided by gamma. At everyday speeds, gamma is close to 1, so the effect is negligible. But as you approach relativistic velocities, the contraction becomes significant. Experiments have confirmed this phenomenon, although measuring length contraction directly is more challenging than time dilation. One area where indirect confirmation appears is in the behavior of particles in accelerators. When charged particles are accelerated to near-light speeds, they circulate within magnetic storage rings. The calculations needed to guide and contain these particles must account for relativistic effects, including the effective contraction of the particle's path. If length contraction were not real, these high-energy systems would not function as predicted. In another example, consider the muons mentioned earlier. From our perspective, They are moving so fast that time slows down for them, allowing them to reach the ground before decaying. But from the muon's perspective, it is not their internal clock that slows down. Instead, the Earth's atmosphere is contracted. It is thinner, shorter, and the distance to the surface is reduced. Thus, they can reach the ground within their brief lifespan. Both views are valid within their respective frames of reference. These effects, time dilation and length contraction, are often misunderstood as being merely observational, like optical illusions or measurement errors. But they are deeply embedded in the geometry of space-time itself. They arise not from how we look at things, but from how nature behaves. The Lorentz transformations are not corrections or approximations. They are descriptions of reality as revealed by experiment. The history of physics shows that many concepts once thought to be absolutes have been replaced by relative measures. Direction, speed, temperature, even simultaneity, each has been shown to depend on one's frame of reference. With Einstein's theory, time and space joined that list. They became interdependent quantities, woven together into a single four-dimensional continuum called space-time. One might ask, if everything contracts at high speed, then how could we ever tell? Wouldn't our rulers also contract, making all measurements appear normal? This is true, but only within a single frame of reference. The key insight of relativity is not about what you see within your own frame, but how different frames relate to each other. You only notice length contraction when comparing measurements across frames, between an observer on Earth and a traveler aboard a relativistic spacecraft, for instance. This has practical consequences. For example, when designing particle detectors or calculating trajectories in modern accelerators, physicists must include relativistic effects in every step. Timing, spacing, magnetic fields, and energy inputs are all influenced by these transformations. The success of these technologies, their precise alignment with theory, confirms again and again that length contraction is not just a theoretical construct but a physical reality. What makes this all the more remarkable is that Einstein's theory predicted these outcomes not by bending to experimental data, but by reasoning from first principles. The insistence that the speed of light remains constant led inexorably to the conclusion that space and time must be flexible. The consequences were not added after the fact. They were there from the beginning, implicit in the postulates. The philosophical implications are just as profound. If space and time are not fixed, then our very notions of distance and duration depend on motion. The universe does not provide a single map that everyone agrees on. Instead, each observer constructs their own version of reality, consistent with the same physical laws, but shaped by their motion through the cosmos. And yet, through all this relativism, there remains a constant: the speed of light. It anchors the structure of space-time, defines the upper limit of motion, and ties together the transformations of length and time. It is the one invariant amid a sea of relative experiences. As we've seen, motion distorts both time and space, but the consequences go deeper than just aging slowly or traveling shorter distances. These distortions lead to an even more surprising conclusion: the concept of simultaneity, the idea that two events can happen at the same time, is no longer universal. In the relativistic universe, what is now for one observer may be earlier or later for another. This challenges one of the most fundamental assumptions of our everyday experience: that time flows equally for everyone and that we all share a single unfolding present. To understand this shift, we must look at how special relativity redefines the relationship between time, space, and observation. In classical physics, simultaneity is simple. Two flashes of lightning strike the ground at different points, and if an observer sees them both at the same time, they are simultaneous. Their timing is absolute, needing only to be corrected for distance. Everyone, everywhere, should agree on the order in which things happen. But Einstein showed that this assumption does not hold when observers are in relative motion. In special relativity, simultaneity is relative. It depends on the observer's frame of reference. Let's explore this with a thought experiment, one that Einstein himself introduced to illustrate the problem. Imagine a long train moving smoothly along a track. In the center of the train is an observer, and standing on the embankment outside is another observer. Aligned with the center of the train, at the precise moment, two lightning bolts strike both ends of the train. From the viewpoint of the person on the embankment, the lightning strikes occur at the same time. The light from each bolt travels equal distances and reaches the stationary observer simultaneously. However, from the perspective of the observer inside the train, things look different. Since the train is moving forward, the observer inside is rushing toward the point where the lightning struck the front of the train and moving away from the point where it struck the rear. This means that, although the light from both strikes travels at the same speed, the light from the front reaches the train observer sooner than the light from the rear. The conclusion? The person on the train does not perceive the lightning strikes as simultaneous. The order of events has shifted, without any trickery or illusion, simply due to the motion of the observer. This is not merely a limitation of human perception. It is a consequence of how time and space are linked in the framework of special relativity. The speed of light is constant for all observers, so the only way to reconcile differing distances and travel times is for time itself to behave differently in each frame of reference. Simultaneity, therefore, is not an absolute feature of reality. It is relative, just like time and space. This realization has deep implications for our understanding of causality, the relationship between cause and effect. In everyday life, causality feels safe and secure. Drop a glass and it shatters. Press a button and a machine activates. We assume that causes precede effects and that the order of events is fixed and universal. Special relativity does not destroy causality, but it does place important constraints on how it works. In relativity, events that are causally connected, that is, one could influence the other, must lie within each other's light cones. This means that a signal or object traveling at or below the speed of light must be able to move from one event to the other. If an event lies outside another's light cone, it is space-like separated, meaning that no signal, influence, or causal connection can exist between them because it would require faster-than-light communication. For events that are space-like separated, different observers may disagree about which happened first. One observer might say event A came before event B, while another says the opposite. Since no cause and effect connection can exist between the two, this reversal does not create a paradox. The order is not physically meaningful. What matters in relativity is not the absolute order of events, but whether they can be causally linked. This preservation of causality is vital. While simultaneity is relative, the sequence of causally connected events remains intact for all observers. If a cause can produce an effect, then that relationship is preserved in every frame. You cannot send a signal to your own past or cause an effect before its cause. Relativity bends time, but it does not break logic. Still, the relativity of simultaneity takes some getting used to. It implies that different observers live in different versions of the present moment. If you are moving quickly enough relative to me, we might not agree on whether two events are happening at the same time. In fact, we might not even agree on what exists right now. This leads to strange and sometimes unsettling conclusions. Suppose you're traveling at near light speed to a distant star. From your point of view, Earth has aged more slowly due to time dilation. But if someone back on Earth tries to describe what's happening now for you, their answer depends on how they define simultaneity. Different definitions, tied to different frames of reference, produce different answers. This has led some physicists and philosophers to propose that past, present, and future are not distinct in any objective sense. Instead, all events exist within a four-dimensional space-time block, and what we perceive as the flow of time is simply the way our consciousness moves through this block. While that view is not universally accepted, it does reflect how deeply special relativity has altered our thinking about time. Interestingly, these ideas are not purely theoretical. They find practical application in fields like astrophysics and satellite communication. For example, when coordinating signals between spacecraft and ground stations, engineers must account for relativistic effects, including differences in simultaneity. High-precision timing systems rely on understanding how different observers in relative motion perceive time and space. Even in cosmology, simultaneity becomes a delicate issue. When describing the large-scale structure of the universe, Scientists often choose a preferred time coordinate based on cosmic microwave background radiation, a kind of universal frame. But this is a choice of convenience, not an absolute reference. In principle, any observer's frame could be used. As we go further into relativity, it becomes clear that time and space are not separate entities, nor are they experienced the same way by everyone. They are part of a unified geometry that adapts to the motion of observers and preserves the consistency of physical laws. This geometry leads naturally to the concept of space-time intervals. While observers may disagree about the measurements of time or distance between events, there is one quantity they all agree on: the space-time interval. This interval combines time and space into a single value that remains invariant across reference frames. Like the distance between 2 points in ordinary space, the space-time interval is the same for everyone, even though its components, time and space, may differ. The invariance of the space-time interval underlies much of relativity's consistency. It ensures that the laws of physics apply equally to all observers, and that the universe has a coherent structure despite the relativity of simultaneity. Ultimately, the loss of absolute simultaneity is not a flaw in our understanding. It is a necessary adjustment, a correction to the assumptions we inherited from classical mechanics. It is not time that has failed us, but our old notions about it. And yet, while special relativity sets clear boundaries on how space and time behave, it also reveals a new one: the cosmic speed limit. As you move faster, time slows and distances contract, but something else happens too. The energy required to keep accelerating increases dramatically. There comes a point where adding more energy does not make you faster, it only adds mass. As we continue pushing our understanding of motion to its limits, one boundary looms larger than any other: the speed of light. Time slows, space contracts, simultaneity breaks down, and yet, no matter how hard we try, we can never quite reach light speed. Why is this? What is so special about this particular value, and why does it act as the ultimate speed limit for everything with mass? To answer this, we must delve into the relationship between motion, energy, and mass, a relationship first clarified by Einstein's special theory of relativity and expressed elegantly through a deceptively simple equation: E equals mc squared. This equation, perhaps the most famous in all of physics, tells us that energy and mass are interchangeable. Mass is simply a very dense form of energy, and energy can, in the right circumstances, be converted into mass. But the deeper implications of this equation reveal themselves when we look at what it means to accelerate an object. In Newtonian mechanics, increasing an object's speed simply requires a constant application of force. You push harder, it moves faster. In principle, there is no upper limit. Just keep adding energy, and you keep gaining speed. Special relativity, however, changes the game entirely. As an object moves faster and faster, its relativistic mass increases. This does not mean that its rest mass changes, the intrinsic mass measured when the object is stationary, but that its total energy increases in such a way that it behaves as though it is becoming heavier. The faster you go, the more energy it takes to keep accelerating. As your speed approaches the speed of light, the energy required to accelerate further approaches infinity. This leads to a remarkable conclusion. It is impossible to accelerate any object with mass to the speed of light, because doing so would require infinite energy. And infinite energy is not available in any physical process or system we know. In this sense, the speed of light is not just a high number, it is a hard limit, an insurmountable wall built into the fabric of the universe. It is important to understand that light speed is not just the maximum speed we have been able to reach so far, it is the maximum speed that any information or influence can travel, according to the laws of physics. This is not a technological limitation, but a physical one. It applies universally, whether we are talking about particles, spaceships, or signals. So what happens as you get closer and closer to that boundary? The mathematical expressions from special relativity show that both time dilation and length contraction intensify dramatically. Time nearly stops for the traveler, and the universe contracts into a narrow, foreshortened strip along the direction of motion. The space-time interval, the invariant quantity between events, preserves causal relationships, but the traveler's experience diverges sharply from those in slower frames. Consider a particle moving moving at 99% of the speed of light. From our point of view, it is already extraordinarily fast, completing vast journeys in microseconds. But if we try to push it to 99.9% or 99.99%, we find that the energy cost grows disproportionately. Every decimal place added to its velocity requires vastly more input energy than the last. Particle physicists deal with this reality constantly. In particle accelerators like the Large Hadron Collider, protons are accelerated to speeds within a hair's breadth of light speed. At those energies, the particle's kinetic energy becomes thousands of times greater than their rest mass energy. Their behavior changes dramatically. They last longer, become more massive in their frame, and move in ways that classical mechanics cannot account for. But no matter how much energy is pumped into them, they never quite reach the speed of light. This is not just a constraint for particles, it also applies to spacecraft, signals, and even hypothetical information transfer. Many popular notions in science fiction, such as faster-than-light travel, warp drives, and instantaneous communication, run headfirst into this limitation. Unless future physics discovers loopholes or alternative mechanisms not yet known, these ideas remain speculative at best. There is another layer to this story, the role of massless particles, like photons. Unlike objects with mass, photons are born traveling at light speed. They do not accelerate to that speed. They exist at it, always and everywhere. But because of this, they do not have a rest frame. That is, it is meaningless to speak of what a photon experiences as it moves. From our point of view, it travels through space over time. But from the photon's hypothetical perspective, if we could even speak of such a thing, there is no passage of time between emission and absorption. A photon leaves a star and is absorbed by a telescope on Earth thousands of years later, but in its own frame, that journey takes no time at all. This leads to another counterintuitive realization. For objects moving at light speed, the notions of distance and duration break down. Photons do not age. They do not experience the passage of time. Their existence is defined entirely by their interactions, where they come from and where they go. Between those two events, their own internal clock does not tick. This asymmetry is key to understanding why we cannot simply become light. To move at light speed would require abandoning mass entirely, something that is not physically possible for any massive object. No matter how hard we try, or how advanced our propulsion technology becomes, the barrier remains. This limit also plays a crucial role in maintaining causality. If faster-than-light travel were allowed, it would open the door to causal paradoxes. An event could, in principle, affect something in its own past, violating the logical order of cause and effect. Relativity's restriction ensures that the sequence of events remains consistent across all frames of reference. The structure of space-time, its geometry, and the speed of light preserves the coherence of physical law. This idea is reflected in the concept of the light cone. Imagine plotting all possible paths a flash of light can take from a single event in space-time. The light cone defines the boundaries of influence. Events inside the cone can affect or be affected by the original event. Events outside it cannot. This cone acts as a causal boundary. The speed of light is the edge of that boundary, defining the outermost possible influence that any signal or object can exert. Within this framework, the structure of the universe begins to make more sense. Galaxies are bound by light travel times. Astronomical observations are bound by horizons, limits to how far back in time we can see. The universe's expansion is measured by how light stretches and shifts as it moves through expanding space. All of this depends on the speed of light being not just constant, but finite. In practical terms, this limit sets the pace for communication and exploration. Even if we built ships that could reach 99% of light speed, messages sent back to Earth would take years, decades, or even centuries to arrive, depending on distance. Real-time communication across interstellar distances is impossible. Light speed enforces isolation. And yet, this barrier is also what gives structure to the cosmos. It protects causality, defines simultaneity, and keeps physics consistent across all frames of reference. If anything could exceed this limit, the logical framework of relativity, and with it, much of modern physics, would collapse. So the cosmic speed limit is not just a frustrating obstacle for ambitious spacefarers. It is a fundamental property of the universe, a law written into the fabric of spacetime itself. Having now understood why the speed of light is the ultimate limit, both physically and causally, we arrive at a curious thought. What would it be like to move at the speed of light? Could one perceive anything? Would time stand still? Would the universe disappear in a flash of brightness, or would everything freeze in place? This question is not merely playful curiosity, it reveals something profound about the nature of light and the boundaries of human understanding. Yet before we try to imagine what the universe would look like at light speed, we must recognize a crucial point. Special relativity forbids any object with mass from reaching that speed, and more than that, it prevents us from defining a reference frame for light itself. In physics, a frame of reference is a coordinate system that allows observers to measure time and space consistently. Every observer, whether standing still or moving, can define one, but only if their speed is less than the speed of light. Light, traveling at the cosmic limit, exists outside this framework. It has no rest frame. In this sense, asking what a photon sees is already a problematic question. A photon has no point of view, not in any definable way. Still, to explore the limits of our own experience, we can imagine what might happen as an object approaches but never quite reaches the speed of light. We can trace the direction that time, space, and light itself seem to go as we close the gap. Let's begin with time. As we saw earlier, time dilation becomes extreme at high speeds. If a traveler were moving fast enough, say 99.9999% the speed of light, then, from the perspective of someone standing still, their clock would tick far more slowly. What might take a few seconds for the traveler could correspond to days, weeks, or even centuries in the outside world. Now, as the traveler moves faster, the rate at which time passes slows even further. In the limit, though never reached, where the speed of light is approached, time would come to a near standstill for the traveler. That is to say, all internal processes would effectively freeze relative to the outside world. The closer one moves to light speed, the more compressed one's timeline becomes. Simultaneously, space itself appears to collapse. Distances in the direction of motion shrink, compressing towards zero as the speed increases. Again, this is from the viewpoint of the traveler. A galaxy that might be millions of light years away in a stationary frame could be only a few meters away in a near light speed frame. The path ahead flattens, folding space into a narrow corridor. The logical consequence of this double compression, time freezing and space collapsing, is that from a photon's imagined perspective, the entire journey between 2 points is instantaneous. No time elapses and no distance is crossed. The photon is emitted and it is absorbed. That is the entirety of its existence, no in-between. This leads to a striking realization. For massless particles like photons, existence consists only of endpoints, an origin and a destination. From our perspective, a beam of light might travel for billions of years across the cosmos, but from the photon's frame, if such a thing could be defined, the emission and absorption are one and the same. This helps explain why photons do not experience decay or aging. They are, in a sense, eternal. Not because they live a long time, but because time never passes for them at all. But let's take another step. What if, hypothetically, we could see from the viewpoint of a near light speed traveler? What would the universe look like? Here, we must consider relativistic optics. As you accelerate, the way light reaches your eyes, or instruments, begins to change dramatically. The effects are not simply about speed, but about how space and time warp your observations. These effects include relativistic aberration, Doppler shift, and relativistic beaming, all of which we will explore more deeply in the next section. But even now, we can glimpse their consequences. From a near light-speed ship, the stars no longer appear scattered evenly across the sky. Due to aberration, light from ahead is compressed into a bright, narrow cone. This means that as you approach light speed, your entire visual field begins to collapse forward. The stars that were once overhead or even behind now appear to crowd into a tunnel directly ahead. It's as if the universe is rushing toward you through a narrowing spotlight. Meanwhile, because of the Doppler effect, the light from those stars is blue shifted, its wavelengths compressed, increasing in frequency. Stars that were once red or yellow might now appear ultraviolet or even beyond visible light entirely. Light from behind you, in contrast, is redshifted, stretched into longer wavelengths, eventually fading from view. The background universe begins to distort. Time appears to stand still, and everything seems compressed in the direction of motion. Though we can never ride a photon, these visual and physical distortions offer a shadow of what such an experience might mean. But what happens to color and brightness as we approach light speed? As more light is focused into a narrower region ahead, intensity increases. This is the effect of relativistic beaming. The brightness of stars and galaxies surges within your forward field of vision, while the light behind diminishes. Your eyes, or your sensors, would be overwhelmed by light in the direction of travel and left in darkness behind. At the same time dilation affects more than just clocks. If you were watching events on Earth from a near light-speed craft heading away, you would see time unfold in slow motion. Conversely, if you turned around and headed back, you would see things unfold rapidly, entire years flashing by in moments. The universe, in short, becomes a deeply unfamiliar place when approached at relativistic speeds. Shapes bend, light curves, distances shorten. Time slows or speeds up depending on your motion relative to the observed object. The sky itself collapses into a tunnel of blinding light ahead, and yet the fundamental laws remain intact. The same equations that govern slow-moving trains and falling apples also govern this extreme distortion of perception. Special relativity is universal. It applies just as rigorously at 5 kilometers per hour as it does at 99.99% of the speed of light. That consistency is what makes relativity so remarkable. It reveals that our familiar world is just a special case, a limited view of a larger, more flexible structure. The rules we take for granted, simultaneity, direction, brightness, color, are all deeply dependent on our state of motion. So while it is not physically meaningful to ask what a photon sees, exploring the world as we approach light speed allows us to glimpse the profound implications of a universe governed by the constancy of light's velocity. It also sets the stage for a deeper question. We've talked about clocks and rulers, but what about the images we actually perceive? What would a camera capture if mounted to the front of a ship moving near light speed? How would the stars shift, bend, and distort in a true visual sense? As we move from abstract thought experiments toward the tangible experience of motion near the speed of light, we find ourselves confronted not only with warped time and space, but with a transformed visual reality. What would the universe look like if you were aboard a spaceship accelerating toward light speed? Not just in theory, but through your eyes or a camera lens. This is where physics meets perception, and where relativity takes on an aesthetic, almost surreal dimension. Approaching the speed of light doesn't just stretch clocks or contract rulers, it bends the very light that defines our vision. What you see and how you see it changes fundamentally. The effects of this transformation fall under the field of relativistic optics, a set of phenomena that includes aberration of light, relativistic Doppler shift, and relativistic beaming. Each of these effects plays a role in reconstructing the visual field for an observer in motion, and together they reveal just how deeply our vision is tied to the geometry of space-time. Let us begin with relativistic aberration, perhaps the most immediate and disorienting effect. In classical optics, aberration occurs when light from a source is seen at an angle due to motion, an effect sailors once noticed when observing starlight through moving telescopes on ships. But special relativity magnifies this effect dramatically. When you move at speeds approaching that of light, the direction from which light appears to come begins to shift. Light from the sides, above, even behind you, gets compressed into the direction you're moving. Your entire field of vision collapses into a tight cone directly ahead. This phenomenon is sometimes called the searchlight effect. At near light speed, the stars no longer appear scattered across the sky. Instead, they bunch up into a bright, glowing tunnel in front of you. This is not just a change in brightness, it's a geometric distortion. Objects that were behind you in your rest frame could now appear ahead, depending on your velocity. If you were traveling through space and accelerated fast enough, the starlight that once streamed from all directions would seem to come from a narrow angle, as if you were flying through a constantly shrinking funnel of light. Next, consider the relativistic Doppler effect, which alters the color, or more precisely, the frequency of the light you receive. In everyday life, we hear this effect in sound. The pitch of a siren rises as it approaches and falls as it moves away. Light behaves similarly, but with far more dramatic consequences at relativistic speeds. As you move toward a source of light, the waves become compressed, their frequency increases, and their wavelength decreases. This shift toward higher frequencies is called blue shifting. At modest speeds, visible light from a star might shift from red to yellow or from blue to violet. But at near-light speeds, the shift moves far beyond human vision. Light from stars ahead of you could shift into the ultraviolet or even X-ray region of the spectrum. At extremely high speeds, it might reach gamma rays. In the opposite direction, light from behind you is red-shifted, its wavelength stretched, frequency lowered. This means that stars behind you would fade, their light stretched out into infrared or microwave radiation, eventually disappearing from the visible spectrum altogether. This dual shift does more than change colors. It reshapes the visibility of the universe. Ahead of you, stars brighten and shift into higher energy bands. Behind you, the sky dims. Your vision becomes highly asymmetrical. The cosmic microwave background radiation itself, normally measured in the microwave band, would be blue shifted into visible light, glowing faintly as a cold, distorted fog. Now layer onto this the effect known as relativistic beaming. This refers to the way light intensity is altered by motion. As your velocity increases, not only is light shifted and bent, but it is also concentrated in the direction of travel. The forward-facing stars become not just visually clustered, but amplified, their light beams directly toward you, while the rest of the sky dims. This makes the area ahead brighter and more intense, like an overexposed photograph, while the rear fades into darkness. This intensification isn't just a trick of the eye, it has real physical consequences. The energy carried by incoming photons is higher, and more of them arrive per second from the direction you're moving. If you were actually traveling at relativistic speeds, your instruments, or even your ship's hull, would be bombarded with high-energy radiation from ordinary starlight. This poses significant challenges for shielding in any hypothetical relativistic spacecraft. The sum of these effects, aberration, Doppler shift, and beaming, means that the sky would no longer resemble what we see from Earth. Instead of a dome of scattered stars, the cosmos would compress into a luminous, color-shifting tunnel ahead of you. Behind, there would be darkness, or at best, a faint reddish blur. To the left and right, stars would smear forward into motion trails. It is worth noting that several simulations of this phenomenon have been developed over the past few decades. Using the mathematics of relativity, scientists and visual artists have constructed renderings of what an actual high-speed journey might look like. These visualizations, while speculative, are rooted in precise physics and serve as one of the most vivid windows into the relativistic universe. One example is the warp-speed tunnel effect popularized by science fiction. While usually exaggerated, it does share something with the real relativistic experience, namely the apparent compression of the universe ahead and the stretching of everything else. But in reality, the effect is not a blur or smear, but a precise, angular reshaping of space due to light's directional shift. Another interesting twist arises when considering moving objects, planets, stars, or spacecraft, rather than static points of light. Due to the finite speed of light and the fact that you are moving through space rapidly, objects will not appear where they actually are. This is because the light you see was emitted when the object was in a different location. This light time correction adds a further distortion. Rotating spheres may appear flattened or even rotated due to the difference between their apparent and actual positions. The object is literally not where you see it. This visual warping is not limited to theoretical thought experiments. It has implications for astrophysics. When astronomers observe rapidly moving objects, like jets from quasars or pulsars, they must account for relativistic effects. In fact, some astronomical phenomena exhibit what is called superluminal motion, objects that appear to move faster than light due to the combination of light travel time and motion at near-light speeds. This is not a violation of relativity, but a clever illusion produced by the very same effects we are discussing. So, returning to our question, what would it look like to approach the speed of light? The view would be breathtakingly strange. The sky would narrow into a bright point. Colors would shift beyond recognition. Stars behind you would vanish. Space itself would seem to blur and twist. You would see, quite literally, a different universe, one shaped not only by what is out there, but by how your motion warps the light coming towards you. And yet, for all this visual distortion, the rules remain consistent. Every photon, every angle, every shift in color or brightness follows the same equations derived from Einstein's postulates. Relativity does not create chaos. It reveals a deeper order, one where perception is shaped by motion in ways both measurable and mind-expanding. In the end, the way we see the universe is not just about the universe itself, it's about how we move through it. Light is not only the messenger that reveals the cosmos, it is also the sculptor that carves our visual reality from the geometry of space-time. Now that we've explored how the visual field warps near light speed, and how light itself becomes an instrument of distortion and transformation, we must turn to a deeper and more perplexing question. What happens to time and space from light's point of view? We've hinted at this idea already, that a photon experiences no passage of time, and that distance, as we understand it, vanishes. But can we truly talk about what light experiences? Does the question even make sense within the framework of relativity? These are not just philosophical puzzles. They go to the very heart of how special relativity treats massless particles and the geometry of space-time. Let us begin by revisiting the notion of a reference frame. In special relativity, a reference frame is a coordinate system in which an observer can assign time and position to events. Observers can be stationary or moving, but the key requirement is that their velocity must always be less than the speed of light. The entire mathematical structure of relativity is built on this principle. This leads to a crucial point. There is no valid inertial frame for a photon. Light moves at the cosmic speed limit, not below it. Therefore, it cannot be at rest in any frame. The equations break down if we try to plug in the speed of light as the velocity of an observer's frame. The transformations that allow us to shift between frames of reference, like the Lorentz transformations, cease to be well defined at light speed. They involve dividing by zero or taking the square root of negative numbers. In short, they collapse. So when we ask what the world looks like from the perspective of a photon, we are already stepping beyond the domain of defined physics. That said, we can still examine the limit, what happens as we approach light speed and what consequences emerge from the fact that light, unlike any object with mass, exists only at that extreme. Let us consider time first. For a photon, there is no internal clock ticking along. It is born when emitted, say, from the surface of a star, and it dies when absorbed, perhaps by a telescope or an atom. From our frame, these two events may be separated by millions or even billions of years. Light from a galaxy at the edge of the observable universe may have been traveling since long before the Earth formed. Yet from the photon's own hypothetical frame, the moment of emission and the moment of absorption are the same. There is no duration in between, no ticking of time, no forward progression. Its journey across the cosmos takes zero time. The photon is not moving through time, it is moving across it, as if skipping the in-between altogether. This idea is startling, but it is supported by the mathematics of special relativity. As an object moves faster and faster, its proper time, the time measured by a clock moving with the object, passes more slowly relative to external observers. At the speed of light, proper time becomes zero. Photons do not experience time, because in relativistic terms, they have no time axis. Now let us turn to space. As an object accelerates toward light speed, the space it travels through contracts along the direction of motion. This is not an illusion or a flaw in perspective. It is a direct prediction of special relativity, confirmed by countless experiments. Distances shrink, paths flatten. At the limit, as velocity approaches the speed of light, this contracted space collapses to a point. So just as time collapses to zero, space does as well. For a photon, the start and end points of its journey are not separated by distance. They are joined as a single event. From this perspective, we begin to see why the concept of motion becomes ambiguous at light speed. To move implies traveling through space over time, but for a photon, neither space nor time exists in the interval between emission and absorption. Its path is defined only by its interactions at the ends. It has no in-between. This explains a peculiar feature of light. While it clearly travels through space from our perspective, it does not seem to have a well-defined position along that path from its own. It does not have a location until it interacts. In quantum theory, this lack of well-defined position becomes even more pronounced. In quantum electrodynamics, the theory that describes how light and matter interact, photons are described not as particles with well-defined trajectories, but as probabilistic entities. They exist as a superposition of all possible paths between emission and absorption. The sum-over-histories approach, developed by physicist Richard Feynman, tells us that a photon doesn't follow a single straight line. Instead, it takes all possible paths, and the outcome we observe is the result of constructive and destructive interference among those possibilities. What does this mean in practical terms? It means that between 2 points, say a laser and a detector, a photon's behavior cannot be fully described by saying it went this way. It went every way simultaneously until the moment it is detected. The classical path, the shortest one, is merely the one that emerges with the greatest probability. In this sense, the collapse of time and space to a point is not just a relativistic idea, it is also a quantum one. Between its two anchor points, a photon does not evolve in the same way massive particles do. It is not a traveler, it is a connection. This interpretation challenges our intuition. We think of light as a beam, a stream of particles or waves moving continuously from source to destination. But this is our view, from within time and space. From the edge, from the limit of velocity, light behaves more like a bridge than a journey. It binds together events, but it does not occupy the space or time between them in the way matter does. There is an intriguing consequence to all this. For photons, the universe does not have a shape or duration. Galaxies are not far apart. The age of the cosmos is not billions of years. Those are truths seen from within space-time, from the perspective of beings who live in it. For light, those ideas are undefined. This boundary state, moving at light speed, acts as a kind of horizon in physics. We can approach it, analyze it, and extract predictions from it. But we cannot cross it with matter, nor can we fully inhabit the frame of light. It is a limit not just of velocity, but of experience itself. And yet, light is central to our experience. It is how we see, how we know, how we measure. It is the carrier of information from the past. Every photograph, every spectrum, every telescope image is a story told by photons, each of them crossing time and space in a blink for them, but delivering meaning to us stretched out across years. In this way, light is a paradox. It is both timeless and our means of keeping time. It is both positionless and how we measure position. It reveals the geometry of space-time by being outside that geometry in a fundamental sense. Physicist John Archibald Wheeler once described light as the messenger particle of electromagnetism, and in doing so, hinted at this duality. Light is a carrier, a courier, but it also stands at the edge of what physics can describe in terms of internal experience. We use light to study the cosmos, but we cannot become light, nor imagine exactly what it would mean to be it. So if we ever find ourselves contemplating a ride on a beam of light, as a young Albert Einstein once did, we should remember that what we're really contemplating is the structure of the universe itself, the way space and time yield to motion, the way limits become rules and rules shape reality. As our understanding of light has evolved through the lens of relativity, we've discovered that time and space collapse to a point for light itself, but the mysteries of light do not end with Einstein. In fact, they deepen. For while special relativity revolutionized how we understand light's behavior at high speeds, quantum mechanics forces us to reconsider the very nature of light, what it is, how it behaves, and whether it even makes sense to think of it as a thing moving through space at all. The quantum story of light begins with a conundrum that puzzled physicists in the early 20th century. Classical wave theory, despite its success in explaining phenomena like interference and diffraction, struggled to explain certain experimental results, especially those involving how light interacts with matter. The most famous of these is the photoelectric effect, an observation that ultimately earned Albert Einstein the Nobel Prize in physics. In this experiment, when light shines on a metal surface, it can eject electrons from that surface. Classical wave theory predicted that increasing the intensity of light, regardless of its frequency, should increase the energy of the ejected electrons, yet the data said otherwise. What mattered was not the intensity, but the frequency. Below a certain threshold, no electrons were ejected at all, no matter how bright the light was. Einstein resolved this paradox by proposing that light comes in discrete packets, or quanta, of energy. These packets, later called photons, carry energy proportional to their frequency. High-frequency photons, such as ultraviolet or X-rays, have more energy than lower-frequency photons like red or infrared. If a photon has enough energy, it can eject an electron. If it doesn't, no amount of added brightness will help, because intensity simply increases the number of photons, not their individual energy. This idea was radical. It suggested that light, long understood as a wave, also behaves as a particle. This wave-particle duality soon became a cornerstone of quantum mechanics, not just for light, but for matter as well. Electrons, neutrons, even entire atoms can behave like waves under the right conditions. This dual nature leads to one of the most famous and counterintuitive experiments in all of physics, the double-slit experiment. First performed with light in the early 19th century by Thomas Young and later repeated with single photons and even electrons, it demonstrates that particles can interfere with themselves like waves, creating patterns of alternating brightness on a screen. Here's how the experiment works. Shine a beam of light at a barrier with two narrow slits. Behind the barrier is a detection screen. Instead of seeing two bright spots, one behind each slit, you see an interference pattern with alternating bands of light and dark. This makes sense if light is a wave. The waves from each slit interfere constructively or destructively, depending on their relative phases. But the real mystery appears when you reduce the intensity of the light until photons pass through the slits one at a time. Even then, over time, an interference pattern still builds up on the screen. How can individual particles interfere with themselves? Which slit did each photon pass through? The unsettling answer is both and neither. According to quantum theory, each photon exists in a superposition, a mathematical combination of all possible paths it can take. It does not decide which slit to go through until it is measured. If you place a detector at one slit to determine which path the photon takes, the interference pattern disappears. The act of measurement changes the outcome. This is known as wave function collapse, and it lies at the heart of quantum behavior. This raises a difficult and fascinating question. If a photon is not localized until it is measured, is it meaningful to say that it traveled through space at all? Was it in one place or everywhere? Between emission and detection, a photon is not a particle following a trajectory like a baseball. It is a probability amplitude, a distribution of possible outcomes. It does not exist in one location, but in a spectrum of potentialities. This perspective aligns curiously with what we saw in relativity. From the point of view of space-time, a photon travels between two events, emission and absorption, with no time elapsing. From the quantum point of view, it does not travel at all in the classical sense. It exists as a connection between those events, its behavior only defined when the journey is complete. This duality creates an ontological puzzle. What is a photon? A particle? A wave? A probability? A mathematical abstraction? The answer depends on the context. In some experiments, photons behave as discrete, countable units, particles that trigger individual detectors. In others, they interfere, diffract, and spread like waves. Sometimes they seem to travel multiple paths at once. Other times, their behavior can only be described in terms of entanglement with other particles. To make sense of this, physicist Richard Feynman introduced the path integral formulation of quantum mechanics. In this approach, a particle does not follow a single path through space and time. Instead, it takes all possible paths, each with a certain probability amplitude. The final result, the path we observe, is determined by the interference of all these possible histories. For photons, this means that between any 2 points, there are infinitely many paths it could take, and the one that dominates the outcome is the one where all the amplitudes reinforce. This is not just a theoretical device. The path integral method gives precise, experimentally verified predictions, matching the results of particle physics experiments to an extraordinary degree of accuracy. Yet the interpretation remains elusive. Is light really exploring all paths, or is this just a way of calculating probabilities? Does a photon exist between source and destination, or only at the endpoints? These questions continue to stir debate, even among physicists. Adding further intrigue is the phenomenon of entanglement, in which two or more particles, often photons, become linked in such a way that their properties are correlated, no matter how far apart they are. Measure one, and you instantly know something about the other. Einstein famously called this spooky action at a distance, but numerous experiments have confirmed that it is real. While it does not allow faster-than-light communication, it challenges classical ideas about separability and independence. Photons, it seems, can share information across space-time in ways that defy local realism. In quantum field theory, the most modern and comprehensive framework for describing particles and forces, photons are not seen as little balls of energy flying through space. Instead, they are excitations of the electromagnetic field. Space is filled with fields, and particles are vibrations or disturbances in those fields. A photon, then, is a quantum of excitation in the electromagnetic field, a ripple that carries energy from one place to another. This field-based view further deconstructs our classical intuition. Light is not a substance or an object, but a dynamic event. Something that happens in the field. Between emission and detection, there is not a thing moving through space, but a process unfolding across the fabric of quantum reality. So what does this all mean for our understanding of light? It means that light challenges every assumption we have about objects, paths, and motion. It is not merely a fast-moving particle. It is not simply a wave. It is not a localized thing, nor a timeless ghost. It is a phenomenon that exists at the edge of definability, revealing itself only when measured and shaped by the act of observation. And this matters not just for theory, but for technology and exploration. Every laser, fiber optic cable, and solar panel relies on the quantum behavior of light. Quantum computing, quantum cryptography, and advanced imaging systems all depend on manipulating photons at the smallest scales. Understanding light at this level is not just about knowing the universe, it is about shaping it. And yet, we must not forget the larger context. Light does not exist in isolation. Its behavior at quantum scales and its role in relativity must ultimately match the real world, where clocks tick, particles decay, and spacecraft fly. If quantum mechanics and special relativity have taught us anything, it is that the nature of light is far stranger than our everyday experience suggests. But for all the theoretical elegance and abstract formulations we've explored so far, science is ultimately grounded in evidence. The equations must match reality. So how do we know these things are true? How do we test such bizarre predictions? Particles interfering with themselves, clocks ticking at different rates, photons existing in a kind of timeless state. The answer lies in the experiments. Over the past century, physicists have developed increasingly precise tools to probe the behavior of light, time, and matter. From massive particle accelerators to sensitive atomic clocks, these experiments do more than confirm existing theories. They also push the limits of what those theories can describe. Light's constancy, time dilation, length contraction, and quantum uncertainty have all been subjected to rigorous scrutiny. And time and again, reality has matched the mathematics. One of the earliest and most convincing demonstrations of time dilation came not from high-speed trains or futuristic spacecraft, but from nature itself, in the form of cosmic rays and a family of particles called muons. Muons are short-lived relatives of the electron, produced when high-energy particles from space collide with atoms in Earth's upper atmosphere. At rest, a muon decays into other particles in just a few millionths of a second. That lifespan, under normal conditions, is so short that a muon traveling at ordinary speeds would never make it down to sea level before vanishing. And yet, when we set up detectors at the surface of the Earth, we find plenty of muons. More than should be there if we assumed Newtonian physics. What's happening? From our frame of reference, those muons are moving at incredibly high speeds, close to the speed of light. As a result, their internal clocks slow down, just as predicted by special relativity. To us, they appear to live longer than expected. This gives them enough time to reach the ground before decaying. From the muon's perspective, however, there is no time dilation. Instead, the distance from the upper atmosphere to the surface of the Earth is contracted. The journey is shorter, so even with a short lifespan, the muon has time to complete it. Both frames are valid, both explanations are consistent, and both confirm Einstein's theory. A more controlled and human-centered test came in the 1970s, when physicists Joseph Haffel and Richard Keating conducted an experiment involving atomic clocks and commercial aircraft. They synchronized 4 highly accurate cesium beam clocks, then placed 2 on planes, one flying eastward around the globe and one flying westward. The remaining 2 stayed at the United States Naval Observatory as a reference. When the flights were completed, all the clocks were compared. The airborne clocks showed different elapsed times than the ones that stayed on the ground, and different from each other as well. The discrepancies matched exactly the predictions of special and general relativity. The eastward flying clock had lost time, while the westward flying one had gained time relative to the ground-based clocks. These results were not huge, measured in nanoseconds, but they were real, repeatable, and matched theory with remarkable precision. This type of relativistic correction is not just an academic curiosity, it is built into the very technology that modern civilization relies on. Consider the Global Positioning System, GPS. GPS satellites orbit Earth at high altitudes and high speeds. Their onboard atomic clocks tick slightly faster due to reduced gravity and slightly slower due to their speed. 2 opposing relativistic effects. Without compensating for these, GPS measurements would drift by several kilometers each day. To prevent this, relativistic adjustments are hardwired into the software. Our phones and navigation systems work because they respect the warping of time predicted by Einstein. On a much grander and more energetic scale, particle accelerators like the Large Hadron Collider, LHC, provide daily tests of relativistic predictions. Inside these enormous machines, particles are accelerated to speeds that are fractions of a percent below light speed. At these energies, their mass increases dramatically, as does their lifetime. Particles that would normally decay quickly persist longer because their internal processes slow down. Detectors around the collision points measure these lifespans, energies, and trajectories with exquisite accuracy, and all the data conform to relativistic equations. These accelerators also confirm aspects of quantum electrodynamics, or QED, the quantum theory of light and electromagnetism. QED is one of the most precisely tested theories in all of science. Its predictions have been confirmed to an astonishing degree, some measurements matching theory to more than 10 decimal places. One famous example is the anomalous magnetic moment of the electron, a tiny deviation from the value predicted by classical theory. Quantum corrections involving virtual photons and particle-antiparticle pairs adjust the value, and experiments confirm those adjustments with microscopic precision. Another set of experiments probes the speed of light itself. It is tempting to think that the speed of light is just a number that we happen to measure, but that's not the case. It is a defined constant in physics, built into the structure of space-time, electromagnetism, and causality. But even so, physicists have tested whether it might vary under extreme conditions. Some experiments have tried to measure the speed of light in different gravitational fields, looking for tiny changes predicted by general relativity. Others have examined whether the speed of photons is affected by their energy, a question related to potential theories of quantum gravity. So far, all results confirm that the speed of light remains constant regardless of the energy or frequency of the photon. And then there are interferometers, devices that split beams of light and send them along different paths to test for changes in timing. The most famous historical example is the Michelson-Morley experiment, which attempted to detect Earth's motion through the supposed ether. Its null result helped lay the groundwork for special relativity. Modern versions, like those used in gravitational wave detectors such as LIGO, operate on the same principle. They measure tiny shifts in the interference pattern of laser beams as space-time itself is stretched or compressed. These instruments are so sensitive that they can detect changes in length smaller than a proton's diameter, shifts caused by cataclysmic events billions of light years away. Once again, these measurements rely on light's constancy and the predictions of both special and general relativity. In quantum optics laboratories around the world, experiments continue to explore the frontier between light and matter. Quantum teleportation, entangled photon pairs, and delayed choice experiments all test the limits of how photons behave under strange conditions. Each result is a data point, a challenge, and often a confirmation of our deepest theories. And yet, the more precisely we measure, the more questions we uncover. Are there limits to how far special relativity applies? Could the structure of space-time break down at the Planck scale, where quantum gravity takes over? Are photons truly indivisible, or are they emergent from something deeper? These questions remain open, and future experiments, using even more powerful accelerators, telescopes, and quantum devices, may provide answers. What we can say, with confidence, is this: the strange, elegant, and sometimes unsettling predictions of relativity and quantum theory work. They match observation. They power our technologies. They are not speculative frameworks, but battle-tested descriptions of nature. And this brings us full circle. From Galileo's ship to Einstein's thought experiments, from photon wave functions to space telescopes peering across the universe, we have used light not just to see, but to understand. It is both a messenger and a measuring stick, a limit and a guide. Yet perhaps the greatest lesson light teaches us is this: the universe is not what it seems. Time is not fixed. Space is not flat, motion bends perception, and reality, when examined closely, becomes something deeper than intuition. Despite the overwhelming experimental evidence confirming the cosmic speed limit, the human imagination continues to reach beyond it. For more than a century, scientists, science fiction writers, and philosophers alike have wondered, what if we could move faster than light? Could we visit distant galaxies in our lifetime? Could we send messages back in time? Could we step outside the causal boundaries that currently bind us? These questions are not simply products of fantasy. They often emerge from genuine theoretical attempts to understand the deepest workings of the universe. While no experimental evidence supports faster-than-light travel or communication, and while such concepts appear to violate fundamental principles like causality, they remain valuable thought experiments. In trying to imagine what lies beyond the speed of light, physicists probe the very edges of our known laws, and sometimes glimpse surprising possibilities. Let us begin with one of the more abstract ideas: tachyons. In the 1960s, theoretical physicists proposed the existence of hypothetical particles that always travel faster than light. These were dubbed tachyons, from the Greek word tachys, meaning swift. In theory, a tachyon would never slow down to light speed. It could only exist on the far side of that boundary, always faster, never slower. Tachyons, if they existed, would have strange properties. For one, they would possess imaginary mass, not in the sense of fictional, but mathematically involving the square root of a negative number. Their behavior would violate our intuitive sense of cause and effect. Depending on the frame of reference, an observer could see a tachyon appear before it was emitted. In other words, it could seem to travel backward in time. This violates one of the key pillars of relativity, the preservation of causality. In any consistent universe, causes must precede effects. If faster-than-light particles could be used to send signals, then messages could be received before they were sent. This leads to well-known paradoxes. The grandfather paradox, for instance, in which someone might send information into the past that prevents their own existence. For these reasons, tachyons remain firmly speculative. No experiment has ever detected them, and most physicists believe they are either forbidden by deeper laws or, at best, unphysical artifacts of certain equations. Nevertheless, their existence in theory continues to challenge our assumptions and stretch the boundaries of imagination. Another path toward faster-than-light motion comes not from particles, but from the structure of space-time itself. According to general relativity, Einstein's theory of gravity, space-time is not static. It bends and stretches in response to mass and energy. In principle, if space-time can bend, then perhaps it can also be manipulated in ways that allow for effective faster-than-light travel, without violating local speed limits. One of the most intriguing proposals of this kind is the Alcubierre drive, a speculative concept introduced in the early 1990s by Mexican physicist Miguel Alcubierre. The idea draws inspiration from science fiction warp drives, but attempts to ground the concept in real physics. In Alcubierre's model, a spacecraft would not move through space faster than light. Instead, it would remain at rest within a region of flat spacetime called a warp bubble, while the spacetime ahead of it contracts and the spacetime behind it expands. The bubble itself would effectively surf across spacetime at superluminal speed, carrying the ship along with it. Because the spacecraft never locally exceeds the speed of light, no laws are directly broken. This proposal is mathematically allowed within the equations of general relativity. However, it comes with serious caveats. To generate such a warp bubble, one would need negative energy density, a form of energy not found in ordinary matter. In some quantum field theories, negative energy can exist under highly constrained conditions, such as in the Casimir effect, but the amounts needed for a warp drive would be astronomical. Moreover, even if such energy could be harnessed, controlling the warp bubble poses additional problems. The original Alcubierre solution required infinite energy to start and stop the bubble, and it introduced issues with information flow and instability. More recent refinements have attempted to reduce these energy requirements and stabilize the geometry, but the challenges remain daunting. Then there is the question of wormholes, hypothetical shortcuts through space-time. First explored in solutions to Einstein's field equations in the early 20th century, wormholes would connect two distant points in space through a curved tunnel-like structure. If traversable, such a tunnel could, in theory, allow for faster-than-light travel by taking a shorter path through a higher dimensional space. Like warp drives, wormholes require exotic matter to hold them open. Normal matter, with its positive energy density and pressure, would cause the throat of a wormhole to collapse. Negative energy, or some quantum analog, would be necessary to keep the tunnel stable. This again raises the problem of sourcing, containing, and shaping such exotic matter. Furthermore, wormholes create their own causal puzzles. If one end of a wormhole moves relative to the other, it might allow for travel not just across space, but backward in time. This opens the door to the same paradoxes we encounter with tachyons. Theoretical physicists have studied whether quantum effects, such as vacuum fluctuations or radiation back reaction, would prevent such time travel scenarios from occurring. Many suspect that some as yet unknown principle of nature forbids closed time-like curves, but no definitive proof exists. At the boundary of these speculations lies string theory, a candidate for a unified theory of all forces, including gravity. In string theory, particles are not points, but tiny vibrating strings existing in higher dimensional spaces. Some models include additional spatial dimensions compactified at microscopic scales. Others propose branes, higher dimensional surfaces on which our universe might be embedded. In such models, gravity might leak into other dimensions, and signals might propagate faster than light in ways not visible to us. These ideas remain highly theoretical and have yet to produce testable predictions, but they offer a conceptual framework in which faster-than-light effects might emerge without violating the known rules of relativity as we currently understand them. It is worth noting that the speed of light limit applies to information, not necessarily to expansion. In cosmology, for instance, the early universe underwent inflation, a period of rapid expansion during which regions of space moved apart faster than light, not by traveling through space, but by space itself stretching. Even today, the universe's expansion means that distant galaxies are receding from us faster than light. This is not in violation of relativity, because the galaxies are not moving through space at that speed. Space itself is expanding. This highlights a subtlety. Relativity forbids objects from locally accelerating past the speed of light, but it does not prevent space from growing in such a way that distant objects recede faster than that limit. In fact, this observation underpins the concept of a cosmic event horizon, a boundary beyond which light from distant events will never reach us, no matter how long we wait. Despite all these speculations, the consensus remains firm. No known mechanism allows for faster-than-light travel or communication within the framework of a established physics, the speed of light remains a boundary not just of motion, but of cause and effect, information transfer, and the structure of the observable universe. Yet the pursuit of such ideas is not wasted. By trying to imagine what might lie beyond that boundary, physicists have uncovered deep connections between gravity, quantum theory, and space-time geometry. They have sharpened our understanding of what relativity really means and where it might break down. In that sense, faster-than-light theories serve the same role as any good thought experiment. They test the edges of knowledge, reveal hidden assumptions, and sometimes uncover new directions for discovery. Having explored the boundaries of speculation, tachyons, warp bubbles, and wormholes, we now return to solid ground. But far from being a step backward, this return offers a deeper realization. The speed of light is not just a maximum velocity, it is a fundamental constant that shapes the structure of the universe. It is written into the very language of physical law, not as an arbitrary number, but as a guiding principle that connects time, space, energy, and causality. It is not simply a limit, it is a blueprint. Let us begin by considering how the speed of light appears in the most important equations of physics. It is not simply the answer to a measurement problem or a value assigned by human convention. Rather, it is the constant that makes the equations work. Without it, the very fabric of physical law would come apart. Start with Maxwell's equations, the set of 4 equations that describe the behavior of electric and magnetic fields. These were developed in the 19th century by James Clerk Maxwell and remain among the most elegant achievements in the history of science. When these equations are combined and solved for a vacuum, empty space, they naturally predict the existence of electromagnetic waves. And more than that, they show that these waves must travel at a certain speed. That speed, emerging directly from the constants of electricity and magnetism, is the speed of light. In other words, light is not an add-on to Maxwell's theory, it is its natural result. The vacuum itself becomes a medium through which electric and magnetic fields oscillate together, self-propagating at a speed determined by the properties of space itself. This was the first major hint that the speed of light was not about the motion of particles, but about the structure of space. Einstein's insight in special relativity built upon this. He took Maxwell's equations seriously and accepted that their predictions held true in all frames of reference. To reconcile this with the principle of relativity, that the laws of physics are the same in all inertial frames, he was led to conclude that space and time themselves must stretch and contract to preserve the invariance of light's speed. The result was a new framework in which the speed of light defined the geometry of space-time. In this framework, time and space are not independent backgrounds in which events unfold. They are woven together into a single fabric, space-time, whose geometry determines how objects move and how clocks tick. And at the core of this geometry lies the speed of light, denoted by the letter c. This constant appears in the Lorentz transformations, in the equation for energy and mass equivalence, and in the space-time interval that remains invariant for all observers. Even more remarkably, the speed of light shows up not only in special relativity, but in general relativity, the theory that describes how mass and energy warp space-time to produce gravity. In general relativity, the paths of light define the boundaries of what can be seen and influenced. The light cone, as we have seen, is the region of space-time that can affect or be affected by a given event. It is not just a visual tool, it is a causal structure, and its shape is determined entirely by the speed of light. Within this cone lies everything that can be touched, changed, or known. Outside, it lies the unreachable. This is how the speed of light becomes a horizon, not metaphorically, but literally. The event horizon of a black hole, for example, is the surface beyond which light itself cannot escape. It is the point of no return, not because the black hole exerts a mysterious pull, but because it warps space-time so strongly that the light cone tips inward. The direction of causality turns toward the singularity. This same concept applies to the cosmic event horizon in cosmology. Because the universe is expanding, there are regions from which light emitted today will never reach us, no matter how long we wait. The speed of light, coupled with the accelerating expansion of space, defines the boundary between the observable and the unknowable. Our universe has an edge, not in space but in time and reachability, and that edge is shaped by the speed of light. So what is this number really? In modern units, the speed of light in a vacuum is defined as 299,792,458 meters per second. But this figure is not merely a product of measurement. Since the year 1983, the meter itself has been defined in terms of the speed of light. In other words, we do not measure light's speed anymore. We fix it as a constant and define our units of space based on it. This reflects a deeper truth. The speed of light is dimension-defining. It links time and space together. In natural units used by some theoretical physicists, the speed of light is set equal to 1, not because it equals 1 meter per second, but because it forms the conversion factor between time and space, between energy and mass. It is worth emphasizing that the constancy of the speed of light is not about photons themselves. Even if there were no light in the universe, the constant CE would still exist. It is the maximum speed at which information can propagate. It defines the structure of causality. It appears in the equations that govern not only light, but also gravitational waves, quantum field interactions, and even the propagation of disturbances in space-time. In fact, in modern physics, C is understood as a fundamental property of the vacuum. It is baked into the structure of space-time in the same way that the number p is baked into the geometry of a circle. You do not choose it. It arises from deeper symmetries. If the speed of light were different, the universe would be unrecognizably different. The relationships between energy, mass, and momentum would change. Stars might not shine. Atoms might not form. Causality itself could break down. So rather than ask why light moves at this speed, we must accept a more profound idea. The speed of light is the speed at which the universe is built. It is not arbitrary, it is essential, and this brings us full circle. We began with the question, what would we see at the speed of light? Along the way, we discovered that this question leads to a cascade of deeper questions about time, space, causality, perception, and the limits of knowledge. We have seen that approaching the speed of light transforms not only our view of the universe, but the very nature of the universe itself. Time slows, space contracts, simultaneity dissolves, photons cross cosmic distances without aging, and everything we see, every star, every galaxy, every scientific measurement is shaped by light's journey across the vacuum. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. Light is at the heart of that comprehension. It is how we see, but also why we can see. It defines what we can know, when we can know it, and how we come to understand the physical world. The speed of light is not just a boundary, it is a law, a constant, a framework, a blueprint for the architecture of reality. And so, while we can never ride on a beam of light, the act of asking what it would be like to do so has taken us on a journey as close to light's nature as we may ever get. A journey not across space, but through understanding. In this way, light continues to illuminate, not just the universe, but our path through it. Our path through it.